tropicalization of modalized spaces. And also, if you've lost a fleece from the MRC snowbird, we have it. Thank you.
Thank you very much. First, I would like to thank the organizers for inviting me, and in the name of all speakers, for organizing this seamlessly put together conference where everything works perfectly except the weather. So let's give them a round of applause. We have to work on the weather issue, but okay. So first, the definition. A Deligne-Mumford curve is a projective, connected, maybe I should use a C, P1, Pn. So I should put Deligne-Mumford-Knudsen curve is a projective connected curve at most nodes. And the PI are distinct smooth points. So here's a Deligne-Mumford curve. So here are the components, maybe some self-intersection, maybe some more interesting self-intersection. Here are some marked points. And, the components should have their own genera. Let's say H1, H2, H3. And the marked point should be numbered. And here are the nodes. And to a Deligne-Mumford curve, the Deligne-Mumford curve is stable if and only if omega c twisted by the sum of the pi is ample. And to a Deligne-Mumford stable curve, we associate a dual graph. I'll usually suppress the p's when I write that. So what do we have? We have a vertex for each component, and I'll write the genus next to it. We have an edge connecting two components for each node. So H has a loop because it has a node with itself, connects with H2, which connects to H3, to the third vertex twice. And I have the marked points, and it's customary to denote the marked points by half edges because they want to be connected to some other curve. And they are numbered. And one on this. Okay. This is a dual graph. So the dual graph is this could be here. So I'll write an underline for the dual graph, and you'll see why soon. So dual graph. And it is a weighted graph. With numbered legs. So these, the half edges might be called legs or ends, or choose your favorite. So weighted graph. So the weights are the weights are a map H from the vertex set of G to non-negative integers. And as I said, the legs are numbered. So that's an old picture. And so the goal of this lecture is to say something about another geometry, and that's tropical curves. So what's a tropical curve? Caporaso and then Ranetti, Mello, Viviani. Not sure about the double letters there. Just one? So that's a dual graph, a metrized dual graph. So what is that? That's a dual graph as before, together with an extra piece of data, a map L, from the edge set of G, where edges don't include the green stuff. From the edge set of G to positive numbers. So
green stuff is the green stuff.
The green stuff is half edges. So they are just there to denote the marked points in the original curve. Okay? So metrized dual graph is just the same as a metrized weighted graph with numbered legs. Okay. So this, you should think of these as lengths of the associated, so L of E1, L of E2, L of E3, and L of E4 are lengths of the corresponding edges. So that's what a tropical curve is. Let me point out here that the curve is, so I'll suppress the points. The curve is stable, can be read off from this data, from the graph. So this is the same as saying that for every vertex, 2h of v minus 2 plus the valence of v is strictly positive. So the number of edges coming out, which is the number of special points on that curve, plus the genus of that curve, plus the degree of the dualizing sheaf of that curve should be positive. That's exactly what it means to be stable. Why are dual graphs important? Let me write it here. Given a dual graph, dual graphs enumerate the strata in, so I should say, we have our modalized space, the Deligne-Mumford-Knudsen modalized space, MGN bar. And in MGN bar, we have strata corresponding to singular curves. And for each G, we have MG bar, which is those curves whose, MG, sorry, not bar, which is curves with dual graph G. And those are precisely the locally closed strata of the modalized space. These are smooth and nice and everything. I'll say something about this a bit more. But Caporaso and her students and collaborators introduced this other geometry, Incidentally, if you have a dual graph, you know what the n is because you have the number of legs. So what is the genus? Let's just point out. The genus of the curve, which
this was introduced maybe 10 years before. But Michalkin maybe should know.
Michalkin introduced it for genus 0, yes.
No, but the tropical curve in the definition that you gave, that's not Caporaso definition.
So let me make an admission. I learned about this a few months ago, and I know very little. This is as much as I know. So, okay. So Michalkin. How do you write Michalkin? Okay. So maybe they did not introduce these, and maybe what they did is add something about the next topic that I'm going to say. So let me just say that the genus of the curve is the genus of this graph, which is just what you think it is. It's h1 of g plus the sum of these h's. So this is defined to be the genus of the graph. And it can be defined to be the genus of the tropical curve as well. So the point about, let's not waste time. So one of the beautiful things about the Deligne-Mumford curves is that they have a beautiful modalized space. And one of the reasons for thinking about tropical curves is that this is another geometry that is associated to graphs, which also has modalized spaces. So maybe that's where Caporaso and the other people have clarified the picture. Will you agree with that? Well, okay.
Of metric graphs, that was done like 20 years ago.
Okay, but not with weights.
With weights. Yeah.
With weights? Okay. Oh, that Voigtmat is a different picture. I disagree. It's a different picture. It's closely related, but it's a different picture. Okay, so let's talk about moduli of. Oh, and we should. So we know when a tropical curve is stable, and it's stable if the underlying graph is stable. Same rule. So it's stable if this is true, so namely if the genus of the vertex is 0, there has to be valence at least 3, and if the genus is 1, valence has to be at least 1, etc. So what graphs are these? These are, I should say, connected in all I'm saying. So these are weighted, metrized, connected graphs with these legs. So let's look at moduli spaces. So the idea behind this does go back to Voigtman and what's the other collaborator? Okay, so how do you construct the moduli space? The easy part is to look at a metric graph where you fix the underlying graph. So if you fix G, then, and if you order the edges, or label the edges, then to give the data of a metrized graph, it just means assign a real number, a positive real number to each edge. And then the moduli spaces. So I'm using moduli spaces in the most naive sense. Okay, just as one-to-one correspondence. Okay. Then I'll call it M0G with, so the tilde is just because I'm ordering the edges. That's R strictly bigger than 0 to the power number of each. So each coordinate corresponds to L of EI. So that's easy. Now, if you want to remove the ordering of the edges, then you can get mg not without a tilde by taking this and modding out by the automorphism group of the graph. So the automorphism, so the modalized space of tropical curves with a given isomorphism class of underlying graph is strictly bigger than 0 to the power number of edges, modulo the action of the automorphism group of the graph. So let's just look at an example. Let's take this example. Let's put a 1 here so that we don't worry about. I could have put, let's put a 0. So what's the automorphism group of this graph? The automorphism group is Z mod 2 squared. Right, you have this switch, and you have this switch. But you note that this part of the automorphism group does not permute the edges. So only Z mod 2, only the quotient Z mod 2 acts on, so that when you order, you have R square, and now Z mod 2 square acts, but one factor of it acts trivially. So the moduli space is, and what's the action of the residual? It flips the two components. So if you start with R bigger than 0 square, and you mod out by Z mod 2, what you get, well, you start by R bigger than 0 without the edges. And mod out by Z mod 2, you get something that looks like this. Fold it up into. This is the M without a tilde. This is the M, and this is the M with tilde. Okay, so now what do we do? I wanted to give another example, which is actually something we will use. Here are two graphs of genus 1. So let's look at the M0G for each one of them. Well, there are no edges here, so the moduli space is a point. Here there's one edge of length L. The automorphism group of this graph is Z mod 2, but it acts trivially on the choice of L. So this is moduli spaces are bigger than 0. So that's just one piece at a time. So if I fix a graph I get a sort of trivially a modalized space. Yes?
The automorphism is supposed to preserve the points or not? I mean, how can you switch the two label points?
So, so I didn't write. So it switches the ends. Switches the ends of each one of these. What's that?
Wanted to mark the ends.
Oh, that's right. So if I mark the ends that I don't have that, yeah. So you're absolutely right. So there's just Z mod 2 in that case. Sorry. Yeah, if I wanted to have something more interesting, I would put a 1 here, and then I would be done. Then I can switch them because these are not numbered. The vertices. Say again?
But then you'll have the R plus the 4.
Oh, then I have a bigger moduli space. Yes. All right. Sorry. Maybe I shouldn't have introduced this example at all. OK. Thank you. Right. So how do we glue cells? We look at what we do with usual curves. OK. So what's a graph contraction? So what you want to remember with the usual moduli space is that if mg is contained in the closure of mg prime, if this stratum is contained in the closure of this, what does it mean? It means that I can take a curve corresponding to this and deform it to a curve corresponding to this, which means that the graph here is obtained by smoothing out. So the curve here is obtained by smoothing out some nodes, namely some of the edges are shrunk. So let me just say what that is. So a graph contraction is maybe the easiest thing to say is what happens when you have a metrized graph, is what you get when you let the length go to 0. So here's one example of a graph. And if you let the L go to 0, this edge will contract to something that has just one vertex, and you add the two weights. And if you have something that looks like this, then so when L goes to 0, you'll replace this graph with this graph. And because of this loop, you'll add 1 to the genus of that vertex. So what this says, can you read over there? Or do I need to lift? Might as well lift this. So what this says is that you can think about the h's of the vertices as sort of tiny loops of length 0 attached to each vertex. And that's actually a very good way to think about them. So now this allows us to glue together strata, in particular these two strata. So let me just erase this. Just continuing on that picture, whenever you have a graph contraction and you choose your ordering of the edges compatibly, you get, so if you have, whenever you have a graph contraction and you choose, did I write this? I completely messed up. So this is a smaller graph than this in the, okay. When you smooth out the node, then this is a smaller graph, a contracted graph. So maybe I'll keep that notation. whenever you contract something in a graph, what was I going to say? What's that? How to glue, yes. And you order things in a compatible way. What you get is so what you want to do is replace so mg naught tilde in mg tilde, which is just r bigger or equal to 0 to the power number of edges. And whenever you have a graph contraction, what you get is a map and a compatible ordering of the edges. You have a map from this to yes. Just by declaring that the length of the missing edges are 0. Okay, so let's do it in an example, and then it will be absolutely clear. So embeds in the locus where L of E equals 0 if E is contracted. So let's look at what happens here. Here there's no issue of automorphisms. Right, so this is G and this is G prime. And the moduli space of order is R bigger than 0. And you have, in this case, you have just an embedding of this in this. Right? So if you put together all the arrows that you have here, you have the arrows that are obtained by automorphisms of graphs, and you have the arrows that are obtained by contractions. You have a big diagram. You have a big diagram of these M, G tildes. Yes? It embeds in the thing attaching, so you're absolutely right. So I should have, so here's the M without a 0. So this is the M0, and this is the M, this was G. This is the M without the 0, and you attach this to this, so these two things both map here. You attach this to this by putting it at the boundary. Thank you. So you have a whole big diagram of all these. So you have where's maybe I'll write it right under here. You have the whole big diagram of all the M G tilde and all the maps associated to contractions, which goes the other way, unfortunately. Oh, I just put the prime here. And I can take the limit of this huge diagram. So this is a direct limit. So the right word, I guess, is colimit. If I take the colimit of this diagram, this is the modalized space of tropical curves. Okay? So you just attach things the way they should be attached. In particular, what you see here is that if you have, okay, so you see this example. If you have So I'm sorry. What's that? Yeah, I'm going to do two examples in a moment. But what I want to point out before I do that, and I just noticed that I should have put a trop everywhere because this notation is confusing with the notation I used, the Deligne-Mumford notation I used here. Maybe I'll use here m g n of g, and then it's clear what I. No, it's the other way around. So this maps the point to r bigger than 0. Right. So here I have. So for modalized spaces of curves, if I take the stratum corresponding to a graph G, it's inside the stratum corresponding to a graph G prime, if and only if G contracts to G prime. Whereas in what I said here, if I take if I take this mg trop, so just to make sure that I distinguish, if I take the, let's write it this way, gn trop of g, then it contains g and trop of g prime. So if g prime is a contraction of g, then in that construction, the closed moduli space where I have the graph G prime is contained in the closed moduli space of the graph corresponding to G. That's what confused you before.
No, yeah, no, the only other thing is that the R, shouldn't somebody be R greater than or equal to 0?
Where?
Because otherwise it's not clear how mg prime actually maps.
So here I have R bigger or equal to 0, yes. So when I remove the 0, I added the boundary. I let the edges, the lengths of the edges go to 0. Oh. And then I glue them together.
What? When you remove the 0, you allow 0.
Yeah, I'm sorry about this. 0 is for open, which is the locus. OK.
Is the diagram missing the maps induced by the automorphisms?
So the maps corresponding to the automorphisms correspond to the trivial contractions of a graph to itself, which are automorphisms. So here I'm just allowing all maps, allowable maps from graphs to graphs.
And the MG is missing a tilde.
This is missing a tilde, yes. So this is what people call the modalized space of tropical curves. All right, so here is the tropical modalized space of tropical curves, one marked tropical curves of genus 1. Right? Looks like this. And maybe the next example, I want to draw it nearby. It will be well, there are more graphs for genus 2. Let me show you M1 2.
Okay, yeah, sure.
Let me show you M1 2. So what are what do genus 2 tropical curves look like? Well, you have genus 1, 2 marked. Did I say it opposite?
No, I asked about the opposite.
But I don't want to do the opposite. I mean, I will not finish with the opposite. So what is M1 2 trop? I'll draw just a few examples. Sorry. I'll draw maybe the biggest graphs, and everything else is their contractions. So here's one. So I'll call this A. No, this is B, and this is A. So I have two lengths to associate to a graph like this. And I have another stratum which looks like this. I call it A1 and A2. So this is a graph with two edges. And so I need R2, and I wonder what I should quotient by. There's a Z-mod 2 automorphism, but it acts trivially. So I have here so this is the stratum corresponding to this, and with the edges, it's the closure of that stratum. So what do you see here? So this is where B. No, this is where A equals 0. So you see here something that looks like. Sorry. This is a B, and this is a genus 1 vertex. What you see here is when B equals 0, and when B equals 0, you just see this. And this is a genus 0 vertex. Here you have R2 again, but you have a Z-mod 2 acting by flipping them. This is the example I had before, and it really is Z-mod 2. So the picture here, I'll draw it below, is this. And they are attached exactly along this locus where B equals 0. Sorry, what am I saying? They're attached along the locus where B equals 0, and which is the same as the locus here, where either A1 or A2 equals 0. So when you let one of these things to go to 0, you go up here, and you are on this locus. So A1 becomes A. Here is the point that looks like this. So what's the point about all this? So we have a geometry, and all the celebrated geometry of the Deligne-Mumford curves. There are dual graphs associated to it. There's a less old geometry of tropical curves, and there are graphs associated to it. And the natural question is, can you connect these two geometries directly? And that's what I want to explain. And I should say that there's a quick explanation, and there's a more elaborate explanation. So I'll try to give you some of the more elaborate explanation, because it actually tells you where things come from. And it's not difficult at all. So why do you expect that there should be an analogy? You expect that there should be, well, there is an analogy, but why do you expect there should be a connection? Because there's an interesting correspondence here on the level of strata, which reverses the order, but still it calls for explanation. The strata of the modalized space of curves are ordered in a way which is completely opposite of the strata of the modalized space of tropical curves. If you think about it, so I'm not going to get into it, but there is in fact a map from M. So this is M12 tropical. And there's a map to M11 tropical, which is this projection. You forget the second marking. You forget the second marking, and you glue the edges to make you stabilize to make a stable tropical curve. And if you think about it carefully, it's in fact true that the fibers are the universal curve up to automorphism. So the analogy is pretty strong. So this should mean that there's a real connection between the two geometries. So I'll try to give a context in which these two geometries are truly connected.
Caporaso, Branetti, Mello, Viviani, in addition to defining this coarse moduli space, they also define a stack.
Not really. So they give it some, yes, they give it some orbifold structure, but not fully. So, I mean, to some extent they give it this. I'm not completely.
Since I interrupted you, can I just say what I meant?
Okay.
So, I mean, this definition as you wrote it, the tropical curve is a metrized Boole graph. That's a standard definition in any introduction to tropical geometry.
Okay.
So who knows who came up with it? But these authors, they looked at this refinement where you add weight.
Yes.
That
Yeah.
was not considered before that, so they did.
Okay.
So the usual tropical curve, that corresponds to a stable curve where every component has genus 0.
Okay.
But they looked at the
Thank you. All right. So I have this word tropicalization, which suggests that I find a way of talking about tropicalization of modalized space. So let's start quickly with the toric variety. So you fix a lattice, and you fix a fan. And you have a toric variety, x of sigma. And at this point, I think, if I understand correctly, there's a slight disagreement in the tropical world. There's one piece of it which will say that tropicalization of the toric variety is one thing, and one group that will say it's another thing. So I think the most common thing you'll see is that the tropicalization of the toric variety is just this vector space. But some other people will insist that, in fact, it should be sigma. And if the toric variety is projective or proper, then there isn't really much of a difference, but otherwise there is. So I'll take this point of view. So in which sense is this a tropicalization? Maybe I'll get to it at the end. But let's take the point of view that the tropicalization of a toric variety is its fan. But we have a problem because the modalized space is not a toric variety. It's quite far from being a toric variety. It cannot be embedded in such a way that its boundary comes from a toric variety. So there's a generalization of the notion of a toric variety, which is called a toroidal embedding, which is originally due to Kemp, Knudsen, Mumford, and Sandona. And a toroidal embedding is something that locally in the étale topology looks like a toric variety. So here's a picture of one toroidal embedding. So take a smooth variety and take some normal crossings divisor. So this is an example of a surface, a smooth surface with two curves intersecting transversely. Here's another example. And Kemp, Knudsen, Mumford, and Sandona associated to a toroidal embedding something that is similar to the fan of a toric variety and reduces to the fan of a toric variety if instead of a toroidal embedding you take a toric variety with its boundary divisor. So I think I'll have to erase this. So the original book of Kempf, Knudsen, Mumford, and Saint-Donat deals with the case where the divisors don't have self-intersection, but other people, notably Caton-Ijol and Thuillier, dealt with a case where there is self-intersection. You can functorially assign to a toroidal embedding a cone complex. So if you have a toroidal embedding, and usually you look at the open set, which is a complement of the divisor, as you associate to it a cone complex. Let me just give you the cone complexes in this particular case. So if I have this surface with, I think it will fit here. If I have the first surface where I have two divisors which are smooth, intersecting transversely at 2 points, each one of these intersection points looks like the toric variety A2, so I associate to each one of these the cone of A2. Each one of the divisors correspond to a ray, but I have two intersections, so I really need to take this cone and attach it to itself. And the only way I know how to draw it is like this. I have one cone here, one cone here. Maybe I'll use the other color. And attach only along the edges. So this is an example of something that there's no way it could be embedded in a vector space, in N. But it looks very much like a fan of a toric variety, except that it's not embedded. It's a little bit more complicated here, because this time you have just one intersection point, but you have just one divisor. So these two edges are really the same. So the picture you have, I like to draw it this way. So this is the edge, and you took the positive quadrant and attached the two edges to themselves, to each other. So that's the cone of, that's the polyhedral complex of this. And it gets a bit more complicated if you have monodromy. So the picture I had before, and unfortunately erased, the picture that looks like this, where I take the quadrant and mod out by Z mod 2 can also occur if you have monodromy. So here's the main result. So if you don't mind, in analogy with a toric case, I'll call this thing the tropicalization of the toroidal embedding. And the main result, which is not hard, I don't know if it deserves to be called more than a proposition, is that the tropicalization of this space is right. So the modalized space of tropical curves is the tropicalization, is the polyhedral complex of the modalized space, the Deligne-Mumford modalized space in this sense. Now there isn't, so that there's an immediate proof, which is sort of the Plummer proof, which is not very interesting, which says that these are glued in the same way. From the same loci, from the same cell. I'm a bit behind.
Right, they should be like topological.
Well, topologically, it's a cone complex, so it's contractible. For a toroidal embedding, you don't get anything interesting in this picture. What's that?
The link is interesting, pathologically.
The link may be interesting. Right, so
What I was thinking, it seems like there's a map from MG, like homotopy class map from MG bar to the tropicalization. Maybe like for the fine one, but it's not very interesting because the thing is contracted. It's always going to be now.
I gather you're right, but it's 5 minutes before the end, so I don't know that I can gather my wits to answer that.
You just ignore that.
So I think I'll skip that proof because I raised the case of M11 bar and M12 bar. So M12, it would take me 5 minutes to show that M12 bar is glued in the same way. I mean, the tropicalization of M12 bar is glued in the same way as the moduli space of tropical curves M12 trop. Well, again, for the sake of time, let me just tell you what I would consider the good answer, which brings up not just the tropicalization as a functor, as something that associates to toroidal embedding a complex, but also a map. So this better answer it builds on the work of Thuillier. Is as follows. I'll drop the bomb. We use Berkovich spaces. So let me say something about Berkovich spaces. In the classical algebraic geometry crowd, I think Berkovich spaces got a bad reputation because they were developed by number theorists in order to resolve hard problems in non-Archimedean geometry, and therefore they have a very difficult aura, just like p-adic Hodge theory, something completely impenetrable, which is completely wrong. What I suggest is you just forget about all the number theorist expositions of Berkovich spaces and just read Berkovich's introduction to his book. And that's beautiful, and you can read it from beginning to end. So it's really not difficult. So what Berkovich spaces do for you is they allow you to, so maybe one picture. So what are points of an algebraic variety? if you have an algebraic variety, then a point is basically an equivalence class of maps from spec of a field to X. If you extend the field, you get the same point. That's why you need an equivalence class. If you take the Berkovich space of an algebraic variety, what's the point of the Berkovich space? Right. It's the same thing, only you take a valued field. Take a field with evaluation. And what does that do for you? You know that when we learn about schemes and varieties, we know that the topology of an algebraic variety is terrible. It's non-Hausdorff, and there are generic points which are not closed, and we learn to live with it. What the Berkovich does for you is it takes this horrible generic point of, let's say, P1, and it stretches it out by allowing you to vary the evaluation on the function field. It stretches it out to a whole tree of points. So instead of having something that looks like this, your original points are sort of scattered like dust. You might remember that from Sam Payne's lecture in the last AGNES. And everything else replaces the generic point. We have sort of a tree of things an infinite tree that connects all these points. So what you get is an arc-connected Hausdorff space with which you can work. So Berkovich spaces are really nice. And one nice thing about them is they resolve this problem that I think I raised here, that the topology of MGN bar and the topology of MGN trop seem to be irreconcilable because things are sort of reversed and don't work the way you want them to. But there's a theorem of Thuillier which builds on work of Berkovich. It says that if you have a toroidal embedding, then you have a canonical map from the analytic space associated to X. Let's say it's proper, so that we don't need to worry about details. There's a canonical map from the analytic space to the tropicalization. Well, which is a retraction. A topological retraction. So this is just a continuous map. So this is in fact a subspace of X analytic. 2005. And since I don't have time, I will not say much about how this works, but I will say this much. So I claim there that the tropicalization is the same as the moduli space of tropical curves. And I want to say just a word about this map. So if this is a homeomorphism, I want to know what this continuous map looks like. And the reason I want to show it is because it's beautiful. So what's a point here? The point here is a map from spec K to MGN bar. K is a valued field. MGN bar is proper, so it extends to spec of the ring of integers. which means that you have a family of curves. Let's ignore the points for the time being. So the rule is, so let's call this P, and this map phi. Phi of P. I need to give you a metrized dual graph. Here it is. It's a dual graph of the special fiber. And I need to metrize it. So I need for each node to tell you what its length is. So here's what L is. So if you have a node, then it locally looks like xy equals f, where f is in R, is in this ring of integers. This is the different R. And L of E is precisely the valuation of f. So what this measures is this map measures the generation of the curve encoded by the dual graph of the special fiber, and it measures how degenerate it is by encoding how fast the functions defining the nodes go to 0. So I better finish here because I'm late.
Are there any questions or comments?
So so how much is about mg in the end? So most of it, it works for any kind of normal crossing situation.
Right. So most of it works for normal. So you have a tropicalization of any toroidal embedding. The point is that you have a concrete and intrinsic description of the tropicalization of the modalized space of curves as a modalized space of tropical curves. You want to ask, why is that useful for anything?
Yeah, that was my
And
question.
so Sam Payne and collaborators, and I have the names here, Coles, Drysma, and Boreva, I think, have proven the Brill-Noether theorem, have given a combinatorial proof of a Brill-Noether theorem using tropical curves. I should say that the tropical curves they used are without the weights, so they were, every vertex had genus 0 in their example.
But can that be done without tropical curves? In the end, there is kind of some.
So this is about, yeah, of course, there is a proof of the Brill-Noether theorem without tropical curves. So, people are working on saying more about limit linear series and things like that using tropical curves. It seems that tropical curves sometimes enable you to distill out of geometric pictures just the amount of information that you need in order to solve something that we're interested in. Sometimes. I don't know how much this is convincing, but.
Are there any more questions?
Okay, we just could get the frame.
Okay, well, let's thank the speaker and the organizers again.